This lecture is going to discuss Chapter 19, Section 6. We're going to be going over Kirchhoff's rules. Kirchhoff's Junction Rule is going to be based on the conservation of charge. It's a statement about the flow of current in and out of a junction. Now, what exactly is a junction? A junction is going to be where you have three conductors coming together. So like right here, you've got three wires coming together. The junction rule states pretty much the algebraic sum of the currents here must be zero. In other words, you don't have current bunching up here at this particular junction. It just doesn't accumulate there. So whatever goes in must go out. So if you've got current coming in this way, you've got current coming in this way, then the sum of those currents must be going out this way. So also, you have Kirchhoff's loop rule, which is based on the conservation of energy and the conservation of electrostatic fields. If you have a loop of current in a circuit like this, and then the entire outside like that, the algebraic sum of the potential differences around any loop have to be equal to zero. Let's go and let's take a look here at the section. So let's not bother ourselves with exactly what all is going on in said circuit other than just what's merely stated here. Again, you have the loop around the outside, you have the loop inside, you have the loop here. Then you've got another circuit here where you have everything going around on the outside. Then you have a current that's going around here on the inside. And you have this loop and you have this loop. Remember, you've got a junction here. You've got a junction here, you've got a junction here and here. Why do you not have one here? And why do you not have one here? You don't have them there because you don't have more than two conductors being joined together. So this is again a summary of what's going on. The current is going to be measured in amps. Also here you have the sum of all of the potential difference around a particular loop. It's going to end up being zero. Two notes here. If you cross a battery from the negative terminal to the positive terminal, then the voltage is going to be positive epsilon, where that's the EMF. If you cross going from positive to negative, then it's going to be minus. So you got to remember these signs as you go about doing this. If you cross a resistor in the assumed direction of the current flow, then V is going to be equal to minus R. In other words, you're going to be dropping the potential difference. If you cross in the opposite direction, obviously you're going to be adding to it. Think of the junction rule as water that flows in from two ends of a pipe and it comes out. You don't have anything accumulating here. The water is all going to run out. So that's the way you also think of current. Also, the electrostatic field is a conservative force field. So suppose we go around the loop measuring potential difference across successive current circuit elements as we go. When we return to the starting point, we must find the algebraic sum of these differences is zero. In other words, when the charge travels in a loop and returns to its original location, the total charge and the electric potential energy is zero. Otherwise, the force would not be considered conservative. Again, you have several examples here to work through. I would encourage you to do that.